Alright, problem number 18, similar to the last one, an archer, aka someone who shoots a bow and arrow. Or I guess just an arrow from a bow. An archer releases an arrow 4 feet above the ground. Oh my gosh, is that like saying H naught is 4? Yeah, it is like saying that. The arrow leaves the bow at an angle of 15 degrees, so theta is 15. To the horizontal, and it leaves with an initial speed, V naught, of 250. And again, we's gonna say, let's not worry about air resistance, because that's gonna make our lives a little more difficult. So let's draw a pretty load diagram that represents this situation. And look, just like magic, we have a little drawing. And so Robin Hood is going to shoot this arrow. Boop, 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 boop. It's going to hit at some X value. It's going to have a height of some Y value throughout, depending on the time. The X value, again, is going to also depend on the time. We know that that angle of launch is 15 degrees, and we know the speed of the launch is 250 feet per second. So there's a nice little diagram there. And now we want to write a set of parametric equations for the path of the arrow. So this is going to work just like that last problem. We need to use the angle 15 degrees, and we need to use the velocity 250 to determine the horizontal and vertical components of this velocity. So the horizontal is going to be 250 times the cosine of 15. The vertical, 250 times the sine of 15. There we have that. So x, remember distance equals rate times time. Well, our rate is the horizontal component of velocity. 250 cosine of 15 times our time. Distance equals rate times time. And y, we have our vertical motion model. So we're talking about feet, so negative 16t squared, plus our vertical v naught, which is 250 sine of 15, times our time, plus our starting height, which we found was 4. So we have now our parametric equations, and it says approximate the maximum height of the arrow. So let's go ahead and graph this equation. Remember to be in parametric mode and in degree mode. So x, we got 250 cosine of 15 times time. Don't forget to close your parentheses. For y, we have negative 16t squared plus 250 sine of 15, close your parentheses, multiply by time, and add 4 to it. Now let's go to our window. Min, let's go 0. Max, I don't know how long it's going to be in the air. Let's try 10 seconds. So 10 for T max. T step, let's go 0.1. X min, we're going to start at 0 again. X max, I honestly don't know how far this arrow is going to fly. I'm going to leave it at 400 like it was in the last problem. I'm going to leave the X scale alone because who cares about that. Y min, I'm going to make 0 so I can see the ground. Y max, I don't know how high this thing's going to go, but it's only a 15-degree angle, so it's probably not going to go that high. So I'm going to leave it at 60 and see what happens. I'll adjust it if I need to. Let's graph it, and holy cow. With the window I just stated, your graph is like, oh my gosh, I'm way off the charts. So that's telling me I need more X and I need more Y, which means, dang, this arrow is going far away. So let's change 400 for X. Let's change that to 1,000. I'm going to change my scale to, I don't know, 100, just so it doesn't get crowded. Y min stays at 0, but the Y max needs to increase. Let's go from 60 up to like 200. I don't know. Scale, let's bump that up to 20. Now let's graph it. And sweet, now I can see my situation here. Graphing it with this new window, I get a graph that looks like that. And wow, I almost have it perfectly for the X maximum, which means, holy crap, this person is shooting this arrow really far. So maybe 250 feet per second is like crazy unrealistic for how fast Robin Hood can shoot his arrow. Or maybe Robin Hood is just a boss. I don't know. But the point is, we have this graph here. And so we want to find this maximum value. And it says approximate, so let's just approximate the maximum value there. So I'm going to go trace. I'm going to move my cursor over, and I'm going to look at what happens. And I can see that when I'm about at 2 seconds, I look to be pretty close to the top. 2.2, I'm still going up. 2.3, oh wait, I'm looking at X values. I'm crazy. So watch your Y values as you move it. Looks like the highest Y value I see is 69.4, which is happening at exactly 2 seconds. Alright, so a lot has happened since I just paused the video. My roommate cooked some sausages, and I ate that, and it was really spicy and delicious. And then I folded a bunch of laundry, and now I'm back. And I'm pretty sure the last thing I said was that at time t equals 2, the y value is 69.4, and that's the highest y value I can find. I don't know, maybe 2.05 is 69.4 also. And it's actually a little bit lower, so maybe 1.95 is a little higher. It's not. So let's go with t equals 2 is pretty much giving us that maximum height, which is kind of convenient. How could we determine if that actually was the maximum height? Well, we could look at the derivative of y with respect to time, dy dt. You can calculate on that on parametric mode. Hit second, calculate, dy dt is option 3. Type in the t value of 2. And see what happens. We get 0.704, so that can't be perfectly the maximum height because that derivative is indicating that we're still traveling up ever so slightly. So maybe we are, I don't know, 2.02? Let's try that. What happens there? 69.41. Let's check that derivative, dy dt. 2.02, and we get 0.06. That's pretty darn close to a zero derivative. Well, why am I looking at a zero derivative? Well, we've always said that the maximum height will occur when the derivative is equal to 0. Now we just need to specify that we're talking about the derivative of y with respect to time. So we can be pretty confident that the maximum height occurs at about 2.02, which corresponds to a y value height of 69.417. Units are feet. So there you have that. And we want to know how long was the arrow in the air? Well, that's saying, yo, dude, find the 0 and figure out what y value gives you that 0. So we could go about and do it exactly, but I'm just going to do an approximation again. We'll talk about how we could do this exactly in a moment. So moving that cursor over, I can see that at time 4.1 seconds, we get a y value of 0.32. At 4.2, we're negative, so we've already hit. So how about 4.12? Let's try that again. Oh, that's a little too much. 4.11. That's too much. 4.1. That's a little not enough. So 4.105. Oh my goodness gracious. That's pretty gosh darn close. 4.104 is even closer. Let's go with that. The arrow is in the air for 4.104 seconds. And I was just tracing two values, trying different times to see how close I could get that y value to 0. And I could, again, get it a little bit closer if I was a little more patient, but I'm not patient. I'm impatient. But how could we do this algebraically? Well, let's go back to number C real quick, letter C. If I took the derivative of this function of y, so let's find dy dt, the derivative of y with respect to time, well, negative 16t squared becomes negative 32t plus, boopity boopity, 250 sine 15 times t becomes just that coefficient, which is 250 sine of 15. Plus 4 goes to 0, so that's gone. And let's set this derivative equal to 0, because that's going to tell us when it's at its maximum height. So what could I do? Well, I'm going to add 32t to both sides, and I get 32t equals that 250 sine of 15. And let's get t by itself. So the time where it's at its maximum height will be 250 times the sine of 15 divided by 32. And let's go ahead and figure out what that value is. So I'm just going to go straight in the calculator. I'm going to hit trace. I'm going to go 250. I'm typing this into the trace. So it says 2t equals 250 sine 15, close my parentheses, divided by 32, enter. And it takes me to the time where t is 2.02202238. So we're pretty gosh darn close before. And it tells me that our maximum height is y of 69.41728. So here we're getting it, essentially exact, and we were pretty gosh darn close up here just with our approximation but I want to make sure we know how to do that precisely if we wanted to. Okay, well, what else? How long was the arrow in the air? Well, that's like saying, well, let's figure out when y is 0. And for that, we're dealing with a quadratic formula thing here, because we have our equation, y equals negative 16 t squared plus 250 sine of 15 times t plus 4. Notice that all we're interested in is the y value here. So since there's not a good way to find a 0 in parametric mode that I know of, what I'm going to do is I'm going to kind of cheat. I'm going to turn my mode back into function mode. I'm going to go to y equals. I am going to graph this equation in my y equals mode now. Negative 16, it's going to be x squared plus 250 times the sine of 15 times x plus 4. So notice I've switched my t's to x's, but you got to remember that now our x values are representing time now. So I'm going to graph that, and what's going to happen? Well, first off, apparently I can't even see it on this window. And think about why that is. Well, look at our window from before. We had our x maximum at 1,000, but now we're talking about seconds. So it'd be much more reasonable to put that at about 10. X scale, let's put that down to 1. Y min, Y max, well, what does Y represent? Y represents the height. How high is this arrow going to go? Well, we know its maximum is at 69. So let's put the Y max closer to like 70. Y scale, put that down to 10. Now let's graph it. Now we can see our parabola, which again is graphing the height with respect to time. So now I could actually, if I wanted to, I can now calculate the maximum height from that last problem. I can actually get my calculator to do that now. So I could have done that problem without a derivative by graphing just the y portion of this equation, which is good to know how to do both ways. But it's going to verify x, it says, is 2.022, which again is telling me the time. And look, that's the same time I found algebraically using the derivative, and it tells me y is 69.417, the same height I found as before. So now I want to find that 0. So I actually need to make my y min negative 5, so I can see a little bit below the x-axis. And now I can go second, calculate. My calculator's thinking still. Second, calculate 0 is option 2. Left bound, type 0. Right bound, type 10 just to get it to the right of it. Guess, hit enter at this point. It don't matter. It tells us that our 0 is happening at 4.104949.7. So I'm going to say that it's 4.105, which is really close to what we found right there. But again, we found it in a different way, which is cool. I could have used the quadratic formula, but I have that ugly 250 sine 15 stuff as my b, and I didn't want to deal with all that. So there you have it. All of these answers calculated in a couple different ways.